This video is on section 6.3, Volumes of Revolution by Zach and Eliza. A solid of revolution is a solid obtained by rotating a region in the plane about an axis. A cross-section is the shape we get when cutting straight through an object or a shape. So if we have a sphere, for example, the cross-section is the area obtained by slicing into the sphere at one point. It's important to remember that we know from section 6.2 that the total volume V is equal to the integral of cross-sectional area. Therefore, V equals the integral from B to A of pi f of x squared dx. The first method we will be looking into is the disk method. Given that we can find the area under a curve between 2 points, A and B, we find the volume of the shape of revolution by rotating this in a circular motion. Now, since the equation of a circle is pi r squared, and each cross-section represents our radius, assuming we are rotating about the x-axis, we find the volume of revolution by taking the integral between B and A of pi r squared, or the equation for a circle. And since we know we can take this constant out, it simply equals pi times the integral from A to B of r squared dr. For our first example, we will explore the volume of revolution about this curve f of x. If we define f of x as x squared, and we take the integral between 0 and 2, we'll set up our equation like this, remembering that the area of a circle is pi r squared. The integral will be between 2 and 0, and since f of x equals x squared, we will have x squared squared, because it's r squared, the whole thing multiplied by pi, dx. So if we solve this integral through, we'll have the volume of revolution between points 0 and 2. So first, we'll take the integral of x to the 4th, is what this simplifies out to, so it would be x to the 5th over 5. Between 2 and 0. And since 0 to the 5th over 5 is 0, we can just put this as 2 to the 5th over 5 times pi, can't forget that, which gives us the answer 32 over 5 pi. For our next example, I will demonstrate how to take the volume of revolution of an object based on the area between two separate curves rotated about the x-axis. So using the same methodology with the radius as before, we could define the radius between g of x and the x-axis as r1, and the radius between f of x and the x-axis as r2. The radius we need to find is the radius between the two curves, which I will denote r3. To find r3, we simply subtract r2 from r1. r2 we can define as the area, as the length between f of x and the x-axis, or simply f of x. Actually, put this as r2. r1 is the length between g of x and the x-axis. So therefore, r3 is equivalent to r2 minus r1, or minus g of x. So now that we've defined R3 as being the length between R2 and R1, we can set up two integrals, one for the volume of revolution between g of x and the x-axis, and one for the volume of revolution between f of x and the f-axis. Subtract them from one another and get the volume of revolution between these two curves. So first, since f of x is further away from the x-axis, we will set up the integral between a and b of f of x squared dx. The squared is, of course, because of our equation pi r squared. From this, we will subtract the integral from a to b times pi of g of x squared dx. This entire thing simplifies down to pi times the integral from b to a of f of x squared minus g of x squared dx. Next, I will demonstrate how to find the volume of revolution between two curves, in this case g of x and f of x, rotate about not the x-axis, but an auxiliary line, in this case y equals -3. So, in the same way as all of our other examples, we need to find this length r. To do that, we're going to have to find, well, first we'll mark this as r2. To do that, first we're going to have to find both r1, which is not the line, which is not the length in between g of x and the x-axis, but in this case, between g of x and y equals -3. And then, of course, r2 between f of x and y equals -3. To find each of these lengths, r2 and r1, all we basically do is take this length between g of x and the x-axis, which is simply g of x, and we add or subtract whatever difference is here. So in this case, we're adding 3, since this is y equals -3, to g of x. So r1 is g of x plus 3. We can do the same thing with r2, marking it as f of x plus 3. And then r3 is simply the difference between these. Now, if we define this curve as being between the points, we'll call this -1, and this, just for the purpose of this example, 1. We can then find the volume of revolution by setting up an integral, same as we did before. So it's going to be the integral between -1 and 1 of pi times r2 squared, which is f of x plus 3 squared, dx, minus the integral between 1 and -1 times pi of g of x plus 3 squared dx. So if we say that it's given that g of x equals x squared plus 2, and f of x equals 4 minus x squared, we can solve out this integral. So if we first simplify it, we say that this is all equivalent to pi times the integral between 1 and -1 of f of x plus 3 squared minus g of x plus 3 squared dx. We can substitute in the values. We can say that this is equivalent to pi times the integral of 7 minus x squared squared. Since we factored in this 3 to the original equation, minus x squared plus 5 squared dx between 1 and negative 1, which then simplifies out to pi times the integral from 1 to negative 1 of 24 minus 24x squared dx which is equivalent to 32 pi. For this example, the theory is essentially the same, but instead of rotating about a horizontal axis, we'll be rotating about a vertical axis, or in this case, the y-axis. So as before, we need to find this value r. To do that, in the same way as before, we'll find the distance between our axis of revolution, or the y-axis in this case, and each curve. So we'll mark for between f of x and the y-axis, we will mark as r1, and g of x and the y-axis we will mark as r2. So to find this distance, we will need to put these equations in terms of y as opposed to in terms of x. So for example, if f of x were to equal x plus 2, we would need to put that in terms of y by simply saying y equals x plus 2, because these are the same thing. And then x equals y minus 2 by subtracting 2 from both sides. This one in turn would be equivalent to f of y equals y minus 2. The equation y minus 2 doesn't define this curve, but just for example's sake, this is how you would switch it over. So once we've put g of x and f of x in terms of g of y and f of y, we can find each r. So to find each r value, you just take the distance between each curve and the y-axis, find the difference, and that's r. To find the difference is simply r equals r1 minus r2. So therefore r equals f of y minus g of y. To then solve the integral, we will say that this curve is between 2 points b and a. And we will create the integral from b to a times pi, because we are still using our equation pi r squared for the area of a circle, of f of y squared dy minus pi times the integral from b to a of g of y squared dy. This of course simplifies to pi times the integral between b and a of f of y squared minus g of y squared dy.